Hey everyone. Let me cue it up. Any questions? Did everyone get their labs turned in before the weekend?
I had technical issues, but Nathaniel helped me out. But he
Okay,
also
good.
had extend the deadline because it wouldn't work on Friday.
Okay. Yeah, Nathaniel's really good with that stuff and sort of helping people along and providing the right feedback and troubleshooting technical things, and because he's been through it all. Nathaniel came here as a freshman at Pacific, and I had him as a student a few times, and then he just was so talented in stats that I coaxed him into staying for his master's, and I sort of talked him out of he's going to go into physical therapy. I'm like, no, just wait. We could use you for a little bit. So he's really helpful for those things. The people who've gone to Nathaniel know that he's very helpful and knowledgeable. So the next one's coming up, right? The next lab we have coming up soon. Let me open up the chat box. So we'll be talking about that more today. It was posted. I looked this morning on the Canvas page, and Lab 2 was posted already, I think like 4 in the morning or something. Nathaniel has weird hours. But so we're here October 12th. Or October 14th, our research topic is due. So make sure you send me your research topic. I know the 2.5 groups topic so far, but a couple more days. This Friday, so coming up, Lab 2 is due, and you could do it by the end of the day. We'll go through it a bunch, and no new readings. You know how many points there are. You know when stuff is due. But again, a lot of stuff is coming up. I have 3 CD certifications so far. If you're not on the list and you sent one to me, just like re-forward the email or whatever. But so I have received 3 so far. The IRB forms, that's not due for a while. You know where to find it. Poster stuff. The poster groups. This group is done, and I have the question. It's a COVID related question. I have everything. Ricky's also done. I have his question, and so then just a little, everybody else have part of a question, and so as we move forward, just make sure you got a couple of days to get these things in, and then just use the labs for what they're designed for, which is to help you along in your poster. If you're having a tough time coming up with content, coming up with a question, coming up with a direction, just go here, just use these, browse, spend 2 hours browsing, and you'll have a database and a question. You'll have everything. It just takes a couple of hours of browsing. Really good one there. Just go there as additional good stuff. Okay, yeah, I'm just seeing the comment that I have an additional group member added. But okay, so we're doing SPSS. We are moving forward in the labs, and we'll soon be moving forward in the research projects. So you know how to use it, the variable view and the data view, those 2 different views where you can manipulate data in different ways. And frequencies, descriptives, you guys are good with that stuff. You've turned it in. That was lab 1, build table 1, right? Descriptives, frequencies, descriptives. And so all that stuff is describing your total sample, the total sample within your study, within whoever you're analyzing. And all of these, remember that William Seeley-Gossett t-test, what that t-value means. You don't have to calculate it. You don't have to recognize this formula on the test, but just knowing the signal to noise, what that means, how to run them, right? Compare means, independent samples t-test. Now, independent samples, that's really all I'm going to make you run, unless you're doing a poster that requires paired samples t-test, and we'll talk about that at some point, I'm sure. Paired samples t-test, that's how you would run it. But for an independent samples t-test, here we're grouping by sex, male, female. I always code males as 0, females as 1, not because females are more gendered or sexed or whatever, but you have to code them as a number. They have to be a number. You can't analyze words, right? You can only analyze mathematically, statistically. You can only analyze numbers. You have to code everybody as something. You can code males as 12 and females as 35. It doesn't matter. what you code them as. But when you define groups, you hit that define groups button, you just list the two different groups you're comparing. T-test, two groups, not three groups. That would be an ANOVA. But here, this is hospital data from the Midwest, giant hospital in Indiana. And just looking at males, females, and blood pressure. So mean arterial is a combination of those two. And what we see, right, females, systolic, now these are hospital patients. This was an emergency department database with a couple thousand subjects in it. And people who are in the hospital now may have higher blood pressure than people who are just sitting at home healthy. But we see males and females have pretty similar systolic values, right? So the systolic difference, we would actually use this one right here because we do not meet Levine's test, homoscedasticity or equality of variances. We don't meet it, so we don't use the top one, we use the bottom one. So that's the p-value we would report, and there's a 24 0.8% chance we would have seen the difference that we did or something more extreme than that if there was no difference, if the null hypothesis is true. Diastolic, that's a pretty big difference, and it actually does meet the assumption of homoscedasticity of equality of variances. So we use the top one, which is the same as the bottom, but we report that top one very significant, highly significant difference of about 3.5 points of diastolic. So that's reading these t-tests, independent samples, t-tests, and this is smokers, yes or no. So 0, I always code no as 0 and 1 as yes. Whenever you're doing yes and no, I always code no as 0, 1 as yes. You can code it however you want. 1 can be yes and 2 can be no. However you want to code it is fine. For consistency's sake, you don't want to have one database be coded in a different way from other databases, because you'll start pulling up, sometimes I'll go through like 8 or 9 databases in a day when I'm running analyses, when it's sort of research season, which it is right now. And I can go through 6 or 7 databases in a day. And if stuff is coded differently in every single database, it's a mess, and it wastes a ton of time of me having to go to the variable view and check how things are coded before I run any analyses. And so I code all of my databases identically. And usually I'll code in the variable view. Because if you see back here where it says sex, male and female, you can code for 0 to list it in the outputs as male, and 1 to list in the outputs as female. And so that's what I do. I just didn't bother to do it for smoking. 0 is no, 1 is yes. And so is there a difference in pulse oximetry, right? You wear one of those, I don't know, I have one here somewhere, pulse oximeters, and you put it on your finger, and then it tells you 98% or whatever your pulse oximetry is. And is there a difference between smokers and non-smokers? The answer is no. Technically, we see smokers have higher pulse oximetry by a tiny, tiny, tiny bit. 0.2 percentage points difference, but it's not significant. We wouldn't reject the null hypothesis. It doesn't fall within that rejection range, but just remember what the significance really means, not just does it fall within the rejection range kind of gatekeeper. Temperature, there's really no difference, 0.942 between smokers and non-smokers. That's like the exact same number. And also no difference in pH, in blood pH. Now notice the N is much smaller here. It's easier to get someone's oximetry and temperature than it is someone's pH. So in any database, you're not going to have every single, there's going to be holes in the databases. You'll have holes of data units. Somebody's going to be missing a height somewhere. Someone's going to be missing temperature somewhere. You might not have a complete data set, and that's okay. So you know what your table 1 looks like. To get these last ones, right, to get these comparisons of categorical data, just remember you go to crosstabs, and then let's compare sex and obesity and smoking. So are males and females, are they different in their percentages of obesity as a yes or no variable? And their percentages of whether they smoke, right? You hit the statistics button and make sure you click on chi-squared. feel free to click on that phi and Kramer's V, feel free. But the chi-squared, that's the important one, so you can actually get your chi-squared. You hit continue, then you click on cells, and if your independent variable, in this case it's sex, the independent variable are smoking and obesity different by sex. So sex is sort of our independent variable. If you put that independent variable here, then columns is the percentage that you would want reported. If sex is up here, then put it in rows. If you just don't know where you put anything, go ahead and click on all of them. Doesn't really matter. You hit continue, you hit OK, and then you're going to get your outputs, right? So um, males and females, obesity, what's the difference? Well, males, 16.3% are obese in this particular sample, which is a pretty huge sample in Indiana. And females, 16.4% are obese. And so the percentage of obesity is really the same between the two sexes. P is 0.994. Fine, that's not interesting. But let's do smoking status, males and females. So males, 31.8% smoke, females, 18.1% smoke. Not quite half, but it's getting close to that halfway point. Is it significant? Yeah, P is less than 0.001. In the larger population, inferential statistics, making inferences about the larger population, there's less than a 0.1% chance that we would have seen a difference this big or bigger if there wasn't between males and females. But the larger population, we would say sort of Midwestern folks who are of the kind of hospital going demographic. So that would be our population. Population isn't just the world over, because we are sampling from Indianapolis. And so you could say metropolitan, Midwestern region. You could narrow it down to where it's not just Indianapolis, right? But it's not going to be rural Wyoming. That's not going to apply to it. It's not going to apply to Alaska. It's not going to apply to Kazakhstan. Or this isn't going to apply to, obviously, to children like 5-year-olds. You're not going to. This is going to be a lot lower. So you have to generalize to the group you sampled from to do inferential statistics. But yeah, among a larger population that this sample characterizes, definitely a difference between males and females in their smoking. So now you have table one all put together. Now your table one, it's not always going to look exactly like this. It's an aesthetic table one, but you can make it look like anything. So this is one of the table ones that I published in pain medicine. And I didn't do the entire sample. I probably did, and then in the peer review process, they said, okay, too much data, let's just compare these two groups. That's probably what happened. When you go through the peer review process, sometimes things change. But what I'm comparing here, there's the p-value, right? Table one, demographics, injury characteristics, and mortality across samples matched for thoracic epidural analgesia. It's people who have rib fractures and stuff. It's something you can do. You get an epidural. People who are, we've heard of those from the context of pregnancy, of delivery, right? If you're at the obstetrician, like yanking out a baby, oh yeah, epidural, whatever. But thoracic epidural analgesia, this is a treatment mode for pain control for someone who comes in with rib fractures. And so this versus that, and the p-value difference. And here's all the variables. You can make your table one look like whatever. Now, table two in this particular study is an even more has even more comparisons being made. So people who received TEA and died, thoracic epidural analgesia, in this particular sample of patients, I don't know, it was 1,300, I don't remember how many there were. Only one of them died. People who received TEA and survived, there were 211. People who did not receive TEA and died, 14. No TEA and survived, 739. And then the comparisons, the information that you need lists down below the table. And so the star, the little asterisks over here where you see there and there and there and there and there. I'm thus drawing attention to significance that lives within the table. In this case, it was people who received TEA and survived, so this group, being compared to those who did not receive TEA and died, so this group. So the p-value is comparing this column to this column. It's not doing anything with these columns. So as long as you're telegraphing your pass, as long as you're like looking at the person you're passing to and say, here, catch the ball, and you throw it right to them, you can do whatever you want with these tables, as long as they're clear, as long as you are describing what they contain. Now, when you move forward in the tables, I get to table 3 in this, and it's a logistic regression, a binary logistic regression. Binary meaning the outcome variable is binary. Every logistic regression is binary. Sometimes they're called binary logistic. SPSS calls them binary logistic. Usually just logistic regression. But and so we're going to go through what this means at the very end of today. We're going to go through what these odds ratios are, exponentiation of beta, what an odds ratio is. There's the p-value. So all you really care about in the logistic regression is these variables. You don't really pay attention to the constant, but we'll talk about it today with the gun database. You report it, but you never mention it, really. The constant's sort of pointless. Unless your data are wacky, then the constant becomes a flag of like, look how ludicrous this is. But it's all of these variables and their independent p-value and odds ratio. So how they affect, in this case, mortality. So what this would mean, reading a logistic regression, age, mortality threshold. So I guess age is I must explain it. It's 65 and up, or something like that. Some particular 80 and up, maybe it was some particular age that is a threshold. So it's a binary variable. 0, they're below the threshold. 1, they're above the threshold. So if they're above the threshold, the odds that the patient will die are 41-fold increase. They go up 41 times the likelihood of death, holding constant. These are all thresholds. So I know the rib fracture threshold is 6 in this particular study. If you fracture 6 ribs, the likelihood of mortality goes up 6-fold, holding constant. Age and treatment. These are the 2 treatments. Mechanical ventilation. Do you like intubate them and artificially ventilate them? And then TEA. Like, do you get the anesthesiologist to inject their backs? And not give them like a spinal, but in the epidural space. And so holding constant everything else, statistically holding these things constant, if you're above the age of 80, I'm almost positive that's what the age was in this, it's a 41-fold likelihood of dying. Use of mechanical ventilation, man, 68 times the odds that you're going to die if that patient is mechanically ventilated. So you want to do everything you possibly can with these patients to avoid mechanical ventilation. Mechanical ventilation isn't what's killing them, but as you get to that stage where you're mechanically ventilating people, that's bad. You don't want to get there. You want to avoid that. If you tumble down that course, that's really bad. So that's what this is saying. The likelihood of death,
Yeah.
variables predicting mortality. Is that a question? All right, just if you don't have questions, just keep yourself muted. But when you see use of TEA, thoracic epidural analgesia, what this means is whether patients are ventilated, hold it constant. Whether patients have 6 or more rib fractures, hold it constant. Whether patients are above the age of 80, hold it constant. Hold all 3 of these constant and just change thoracic epidural analgesia. And what we see, the odds ratio, there's a 97% reduction in mortality. And so when you see the negative sign, that means it goes down. And so it goes up, goes up, goes up, goes down. There's a negative sign. And the odds ratio, an odds ratio of 1 means nothing happens. Multiply anything by 1 and it's the same number, right? So what are the odds that you're going to die? Well, this affects my odds by 1. Well, that's the same thing, right? You get the exact same number. 50 times 1 is still 50. So when you see these numbers less than 1, you're reducing the likelihood, you're reducing the odds that you're going to die. In this case, you have like a 97% chance of mortality is reduced by using this particular treatment. So that's what your odds ratio means. Now, before you get to logistic regressions and linear regressions and maybe negative binomial or whatever other interesting analyses you do, start with the bird's eye view, right? Start with the bivariate correlations, and this will inform your statistics. So correlate, bivariate, just drag everything over, whatever you want, just drag it all over. And you know what to look for here. You've done this lab. Diastolic associates with systolic very strongly with a very low p-value, right? Pulse pressure associates, it should associate with all those blood pressure things. Temperature associates very weakly but significantly with age. So you know what those correlation coefficients are, and maybe it's a point biserial correlation. Usually in that particular output, it was all Pearson correlation coefficients, continuous to continuous. Okay, let's get into where we left off yesterday with a little bit of reminders of, some review still to do. But just remember that what I am not talking about, no part of what I'm saying is about the emotions and the devastation of crime and the victims of those crimes. Now, war is sort of a socially sanctioned activity. We all just sort of accept it. I don't think the soldiers are as pleased with our, oh, it's war, it's nothing, right? But school shootings, it's just avoidable tragedy. War, maybe that's not unavoidable, but this isn't this is neither history nor sociology, and certainly not like PTSD psych class. We're talking about statistics. And so all I get to talk about and all I care to talk about, because anything else I'm just going to offend people, all I care to talk about is where I get to shrug my shoulders. Ethically, I get to shrug my shoulders and say all of this that everyone's saying is stupid, right? You turn on the news after any shooting. I do it every time just to see if humanity has evolved academically to such a state that we can talk about phenomena without lying about it, right? So don't just discharge statistics as though they are indiscriminate, organic, earthly matters. These are matters of human intervention, and when you manipulate them to your liking, you manipulate findings to elicit support for your already established position. That's terrible, right? That's ridiculous. That's what education should purge. And that's what we're trying to do in this class, is to make sure that when you encounter statistics, you can appraise them. You can appraise, is this legitimate, or is this person just lying at me? Are they just boasting and yelling and trying to bulldoze me with a fake position? And that's usually what happens on the news. I don't know, how often, or what political party does it more, or what. I don't have any sociological commentary. All I have is a series of encounters. I'm 40 years old, and for the last 20 years I have been badgered with false information. When I go to the doctor's office, when I turn on the news, it's just false information everywhere. And I found myself for years saying, well, actually, and then it just pisses people off. Go to the doctor and explain to the doctor that they don't actually know what they're talking about. I get that you went to medical school in 1989, and cell signaling, wasn't understood back then in its current state, and so you really don't know anything about metabolism or how these drugs might work. But technically, go try to correct people, and they dig in their heels, their voice gets louder, they get a shaky sometimes. They got like the vibrato of an opera singer, but it's coming from agitation. And people don't like to be wrong. What we like to do is win arguments. People don't really care. You'll notice, just pay attention. People don't really care about truth. What they care about is victory. People care about winning. They care about winning an argument. They don't care about coming out of the argument a smarter person who understands phenomena more clearly, and what you thought was right before is now wrong and you're smarter for it. That's not really how people behave. Have you ever corrected a doctor with your research on metabolism? Oh, yeah, all the time. Um, but I got so sick of doctors. They don't really know anything about physiology. Now, doctors are way smarter than me in matters of, they can pronounce correctly 150 prescriptions on what given, illness. But, like I teach physiology, and every year you have to update your understanding of it. And so I can usually tell, I can't tell the exact year a doctor graduated. I can't say, like, you graduated in 1994, or you graduated in 1996. I can usually tell what presidential administration they graduated in by what they believe is true that's actually false. All right. Yeah, all right. I'm done. I'm done talking about that. But what you want to do, is have truth, and you don't want to cling to that truth so vigorously, where your knuckles are white and your hands are shaking and your voice is in its vibrato of agitation. You don't want to do that. So a good place to start is explore data, right? In this case, we're exploring the gun database. And so, right, these are the variables for the country by country one. And just drag all the continuous ones over here. If you have dichotomous or some sort of nominal, it doesn't have to be dichotomous, but some sort of nominal country size or whatever, if you want to separate it into quantiles or something like that, drag them all over there. And then you hit the statistics button and click on descriptives, right? So that'll give you all the descriptives, hit the continue option, go to the plots, and those three, just histogram and normality plots with tests, put those in there, hit the continue, and then you hit options and exclude cases pairwise. This doesn't really matter. This is my preference, and I would suggest it be your preference. It doesn't have to be. There's nothing wrong with listwise. Listwise just does a cruder purging of variables. If you're missing data points, remember the pH. There was the pH, and there were fewer subjects who had that than had temperature or who had pulse oximetry. If you have missing data and you do the listwise, you're purging, you're dropping, you are omitting more data. Than if you do the pairwise. Pairwise, it just eliminates the data that's the comparisons that are missing, but it retains that row, it retains that subject and the rest of the value. So I always do exclude pairwise because you get more data out of it. Potentially, you get more data out of it. Depends what your database looks like. But when I work with medical databases, it's easier to do it this way to get as many interactions, as many comparisons as you can. It is fine to do listwise. It's totally fine, whatever you want. This is my preference down here. Hit continue, and right, this is the last version of SPSS. The new version of SPSS looks like that. It's the exact same information, the same numbers and percentages, and all of these things are the exact same. I mean, if you just look at this one, it's a little bit sloppier looking. The new one is a little bit tidier. All the data is the same, and the data are the same. But as you run your own analyses, just don't rely. This is what I was saying last time. Don't rely on any one particular um, visualization of the output. When anyone, here's the fonts and where the colors are and where the data are arranged. What you want to do is be able to read the data, no matter how it's presented to you. You want to be able to read it because journals aren't going to put this in there. They're not going to copy and paste in an SPSS output. So as you read journals, just like my table one, you saw my table 1, 2, and 3. They don't look like SPSS for that one particular study. Everything I do has a different looking table one, but so you don't want to get too used to it. So the first thing that comes up, those descriptives, right? And when you do the explore, so this is exactly what you're going to be doing for your lab 2, which is due on Friday. And but when you see, the mean and the median, the variance, the standard deviation, the minimums and maximums, and skewness and kurtosis and all stuff, the new one is tidier. Sure, the information is the exact same, right? So this is the latest version of SPSS. That output that was on the previous slide, that is the second to latest version of SPSS. It just changes. Now this, when I say the latest, that is as of today, right? Next year, maybe it looks different. So don't rely too heavily, too vitally on a particular visualization of the data. But mean and median, you want those to be close, and it'd be nice if they're the same number, but you want them to be close. If the variance is huge, that's problematic. Over dispersion versus under dispersion. Over dispersion, you have this giant variance, and you know what variance is. So skewness, kurtosis, remember a narrow range. If it's 0, you have this beautiful curve. If it's 3, 4, 5, we're getting into skewness and kurtosis. Skewness is the tail. Is it skewed? Is it sort of dragged in one direction? Is that tail being yanked left or right? And kurtosis is how mountainously peaked it is. Is it a plateau? Is it like a very pointy leptokurtic? So that's platykurtic is over here. Leptokurtic and very thin. The tails, there's the question, what do the tails mean? And so the tail is just going to be, like for financial data, you're usually going to see this. Hospital data, I always see skewed right, which is why I report my skewness when I do. I did one paper, I'm sure I've mentioned it before, on the cost, just like I was showing that logistic regression on the odds of mortality. That was that table 3 I showed earlier. I did the next paper I put out in the exact same journal was on the cost of care and thoracic epidural analgesia. But the cost of care looks like this. It's always skewed super far to the right because so many patients are billed, $50,000 or something like that. And then there's like, it just like nobody's billed negative money, right? And so you have this abrupt, very steep, um like cliffs of insanity from Princess Bride, like steep. And then there's just the cost of care depending on how long you stay, mostly, and you know what was done to you. There's going to be like a $2 million patient, $1 million patient, and $900,000 patient. And so that's what this means, is you have these outliers dragging your bell curve in one direction. So a large skewness of, 5 and 6, and some of these skewnesses that really drag it in the positive direction. Now it could also drag it in the negative direction. I just for the types of analyses that I do, the types of databases that I get, I I don't encounter this very often. I usually encounter this. Tests of normality, remember, so if you're going to have a larger sample, use your Smirnoff. I don't know how to remember that. I'm sure there's some sort of like fraternity, sorority memorization tool for that one. For the smaller samples, of which this is, right? This isn't a huge epidemiological survey of 50,000 people or something like that. Go ahead and use a Shapiro-Wilk. This just means significance, and every one of these variables means normality. We do not get to assume normality when we see significance less than 0.001. So bigger tail equals more outliers. Yeah. And it's not necessarily about the correlation. So bigger tails equals more outliers, less correlation, question mark, right, in the comment box. And it's not necessarily how correlated something is as much as do we get to analyze that? A lot of these analyses have assumptions, and we'll start talking about these assumptions, whether you meet the assumptions of ANOVA and whether you meet the assumptions of regression. And we've talked about this a little bit, homoscedasticity, stuff like that. You're expecting relatively normally distributed curves. The worse your distribution looks, the less reliable your statistics become. So even if you find these nice p-values, they're not really trustworthy. And when you look at the Shapiro-Wilk, what a nice thing to report here, that nobody on the news is going to report because their veins are throbbing in their neck as they boast in either direction, whatever they're claiming, is in the tests of normality, Shapiro-Wilk, what we find is distributions that are not normal. That's all you have to say. Like, we didn't pass the tests of normality. Shapiro-Wilk, p is less than 0.001 for everything. So that was the old one. This is the new one. It's the exact same stuff, right? So it's the same numbers, right? So there's the same variables over here. These are the same values over here, but it looks a little bit different. The table itself looks different. Histograms, right? Skewed right. So there's like nothing, and then it just gets, so it's a positive skew. So it's skewed right in this direction. If you want to look at the new histograms, that's the SPSS you probably have. Now, sometimes people can get SPSS for free. The name Shapiro-Wilk, just people, those are just like statisticians and mathematicians and like, just like you go into medicine and everything's just named after people. Look up Chadwick's sign. Chadwick is the guy who, discovered that one. Google that. You're all on the computer right now. Everything's just named after usually like some guy. And so that's what these names of things are. Usually you're just, Pearson correlation coefficient, Carl Pearson, right? People like to, it's the planting of a flag. I conquered this nation. Here's my flag. I mean, that's all people are doing. I conquered this statistic. I discovered this medicinal thing. I mean, sometimes people don't really want to have like Lou Gehrig's disease, ALS, like Lou Gehrig was probably not, ooh, me. But the way things get named, people tend to be egomaniacs who put their name on everything. I think that's what the question meant. So those QQ plots, those quantile plots of what the guns look like. Here's the old version in SPSS. Here's the new version in SPSS. There will be a newer version that'll come out next. So again, just you look at the labels of things and understand the statistics, not just like, okay, where exactly do I look in this particular graph? No, understand what's there, and you'll go farther in your I guess it's not really a measurable distance. So you'll go further in your understanding of stats and science and what is, true. Um, uh, Again, the exam score, this was our exam score compared to guns. Now, activity on Canvas, this isn't very good. So it's not all that helpful to use Canvas activity in these analyses, right? It looks a little bit like the gun data, Canvas activity, and probably because some people just log into Canvas and leave it, and they're gone, and they go do something else, and they log, they turn on the computer the next day or something, and I don't know, I don't know what the Canvas activity. It's not a nice distribution though. Um, the thing that's closest to a nice distribution in the gun database is percentages of homicides by guns. Now, that's not good. That's not like a good one, but that's way closer. Look at this. It's like a right angle. I mean, this is like these things look horrible. And just for these other four variables that are in the database that you have that was posted last night, early this morning. So graphs, yeah, you don't really need to do graphs in SPSS, but if you decide to, chart builder, and you just like click around and drag stuff in and hit OK. Remember, this is what that graph looked like, the scatter plots, right? Guns per 100 people versus total homicides by guns. And so we get some outliers. That's the US, that's Brazil down there. Here it is in the brand new one. Same thing. It's the exact same graph, except it's the newest version of SPSS. This is SPSS 26. I don't know if there's something newer. 26 is what I have currently. I've gone through, I think I had like SPSS 10 or something. And so this thing just keeps renewing all the time. So regression, getting into regression, which is where we left off last time. I did this very brief glimpse at a simple linear regression at what this is doing. Tell Gianna hi for me. Hi from Gianna. I'm guessing that's Merigliano Gianna. Give her my sincerest, warmest greetings. So you analyze and go linear, right? Because we're going to do a linear regression. Linear regression means a dependent variable is continuous. There's a continuous dependent variable. The independent variables can be whatever. Your predictors in a regression. Doesn't matter what they are, but the dependent variable, your outcome, this is a univariate analysis, meaning one dependent variable. Linear means that one dependent variable is continuous. Now, binary logistic, that's what I showed earlier in that study about the odds of mortality, what affects the odds of mortality. That's a binary logistic. So that's your dependent variable is going to be dichotomous, binary logistic regression. It's a binary dependent variable. Your independent variables can be continuous, they can be whatever. Binary and continuous doesn't matter. So a simple linear regression is you have one predictor and you're always going to have one dependent unless you're doing multivariate analyses, but we're just for this class, we do univariate analyses, single dependent variable. You can have a bunch of independence in a univariate analysis. Univariate means dependent. Multivariate would mean multiple dependent variables all at once. So your independent, let's do guns per 100 people and number of civilian gun deaths. And you'll all talk about if you want to do the 95% confidence interval, I'll show you where that is. But for this, let's just look at the basics. So you hit OK. You put those two things in, say OK, you get your R squared. And that is the percentage of variance that you can account for in this particular relationship. So in your dependent variable is whatever it was, civilian gun deaths or something. Number of civilian gun deaths, that's your dependent variable. The R is saying this is all over the place. Some countries have a ton, some countries have a little bit. There's a lot of variance, there's scatter. This is just not like everyone gets the same value. Every country is all over the place. There's variance. How much of that variance can we account for with this predictor? Oh, a little over 25%, 27.4%. But who cares, because these data don't really lend themselves to regret. I mean, these bell curves look horrible and stuff, but this is what the R squared is telling you. If the data are sound, that's what the R squared means. The adjusted R squared will go down if you start putting in more and more predictors, and those predictors aren't adding predictive capacity, if they're not improving your ability to predict your dependent variable. the adjusted R square will go down, but just report the R squared. You don't need to report the adjusted R squared unless something fishy is happening. And the ANOVA table, just look at this. This is just the predictive power of the model. But in a simple linear regression, the predictive power of the model is the exact same as the predictive power of the single independent variable that's in there. Now, if you're running a multiple linear regression, that's not multivariate, that's still univariate, but a multiple linear regression just means multiple predictors all in the same model, then this value is going to be more meaningful. Right now, it's just the exact same thing as this. So what this is saying, right, we'll pay attention to the constant in a minute. You never actually talk about the constant in a publication, because when you do publications, you want to make sure your data are sound before you publish. And you're talking about the constant, the only reason to do that is like the data are weird and messed up. And so if people refuse to mention what the constant is, put this in your tables. So put the constant in your tables. But the constant it's sort of irrelevant. It's supposed to be sort of meaningless. And it's the y-intercept. I'll show you what that means in just a second. But down here, when you see the unstandardized beta, this is the effect of a 1 unit increase in your independent variable, whatever the unit is. If this were body weight, if it were pounds of body weight, it would be a 1 pound increase. If this were dollars of annual salary, this would be a $1 increase. If this were pH, right, it would be a 1 unit increase in pH, which is a ton. If this were BMI, it would be a 1 unit increase in BMI. As guns per 100 people, what that means is a 1 unit increase in guns per 100 people. Let's say one country has 10 guns per 100 people, 10% of people. It wouldn't be 10% of people, but it would be like 5% of people have 2 guns or something. But there's one gun for every 10 people, something like that. Well, let's go to 11 guns per 100 people, and then 12 guns per 100 people, and then 13 guns per 100 people. That's what these values are based on, a 1 unit increase in your independent variable and your predictor. People in regression, people usually refer to the independents as predictors. They are your predictors. It's fine to call them independents. I think I mentioned earlier that when you're running a multiple linear regression, a lot of those independents aren't actually independent of each other. They can be correlated with each other. And so people have taken to calling them predictors as opposed to independents as a matter of accuracy of nomenclature. But it doesn't matter. You can call these independents or predictors. Predictors is preferable and more common in the literature, but it's fine. It doesn't really matter. So a 1 unit increase in your predictor elicits this effect in your dependent variable. In this case, your dependent variable is number of civilian gun deaths. So, and then your significance is over here. So what this is saying is a 1 unit increase in guns per 100 people. So let's say you go from 11 to 12 guns per 100 people should elicit a 909,709 additional civilian gun deaths per year effect. P is less than 0.001. This is ludicrous, but what it's saying, this is Bill Heron had that snicker test. Remember the like, oh, come on. That's sort of like, you make a facial expression and sigh, or maybe suck air in through your teeth. You make some gesture of this, just, I can't believe this. Yeah, I'm seeing statistics that the numbers look impressive, but come on, right? That's the snicker test. When you see something like this, with each additional gun per 100 people worldwide, any country, any particular country increases guns per 100 people by 1, there's almost 1 million additional civilian gun deaths. And that's a P is less than 0.001. So if the null hypothesis were true, meaning civilian gun deaths and guns per 100 people had nothing to do with each other, if the null hypothesis were true, there's a less than 0.1% chance that you would have observed something this big or bigger. Something, there's, I don't know what the P is, but it's certainly less. It's actually less than 0.0005. Otherwise, it would round up to 0.001, but it's certainly less than a 0.1% chance that you would have observed an effect of over 900,000 annual civilian gun deaths, or more extreme than that, 1 million, 50 million, if the null hypothesis were true, meaning those two have nothing to do with each other. That's ludicrous, right? So this is the new output. It's the exact same numbers. exact same numbers, but this is the latest version of SPSS. It's the same numbers. It has a different aesthetic. It looks a little prettier. They painted it a little bit in black and white and blue, but it's the same exact numbers, same thing. You see this 909,709. And again, there's the constant. Now let's look at what that constant means. The beta 0, right? So that is the y-intercept. That's what that's describing, the constant or the y-intercept. It gets reported as beta 0, beta 1, right? That's this right here. So this is it, retaining our coefficients box, right? This is the same box from the last slide. Now, here's the y-intercept. We begin with negative 5.6 million civilian gun deaths every year. So every year, we have 5,653,500 people being revived, like Lazarus syndrome, or people just returning from the grave. I mean, this is like The Walking Dead. Okay, there's 6 million people re-enter your country every single year just from the tomb. That's what this analysis is beginning with. And then with each additional gun per 100 people, you're going to increase by 1 million people. So nearly 1 million. So you go from, why is that the constant is a question, because the data are terrible. These data don't lend themselves to regression analyses. None of the distributions of the data are so ugly that you don't actually get to run these things and trust them. What you want to see is a constant the constant's never going to be like where exactly it's supposed to be. And that's fine, right? It's never going to be like, oh, here's exactly what the constant should be. That's not going to happen, but it shouldn't be negative 5.5 million gun deaths. I mean, it just gets so ludicrous, but people don't report that. When they come onto the news, they say, every single additional gun, you're killing 1 million people a year. Oh, fuck you. Like, this is so ridiculous. Like, okay, but you add one more gun and we're still bringing back 4.5 million zombies. That's when people on the news are declaring their research findings. They don't report the limitations. They report the findings, and the limitations negate any finding they could have. How did they come up with this? It looks like nonsense. What should it look like? So, all reasonable questions in the chat box where, what should it look like? Now, think about something like this. Let's just illustrate. Let's make up something and illustrate what the regression should be doing. It's Stockton outside, or wherever you are. I don't know where you are. For me, I'm looking out my windows and I'm looking at Stockton, and it's like a sunny day. It doesn't look like Mordor outside finally, and right across the street, let's say there's a 2-bedroom house. The house next door maybe has 3 bedrooms. Where I'm standing, there are 3 bedrooms. Let's say there's a 1-bedroom house down the street. And then there's like a 4-bedroom house. Let's say just this neighborhood, let's say it has a bunch of different numbers of bedrooms. And you begin, what is your monthly rent? Now, ignore the numbers. Your rent isn't going to be like $5 million or negative $5 million. That'd be wonderful. I could just live for 1 month here and then retire. But so what we see is, like, with each additional bedroom, you expect your rent to go up. Okay, so if it's like 0 bedrooms, it's like some studio that doesn't have bedrooms in it. The monthly rent, maybe it's like $700 or something like that for some like no bedroom studio in Stockton. And then you go up to 1 bedroom and the average price goes up, and now it's at 1,000. And you go up to 2 bedrooms and now you're at 1,300. And you go up to 3 bedrooms and now you're at $1,600. That's what a simple linear regression is showing you. 0 bedrooms, right? We're crossing the y-intercept over here. And so it'd be like, $800, $700, whatever. And then with each additional bedroom, with each additional 1 unit increase in your independent, number of bedrooms would be your independent variable. Your dependent variable in this analogy would be how expensive is your rent. So independent, or your predictor, would be number of bedrooms. Dependent variable, cost of rent, monthly rent. And so you would see the constant, $500, $600, $800. But you're gonna miss the mark, $100, 2,000, whatever. Who cares what the constant is? If it's ludicrous like this, where it's just everybody becomes Lazarus and is now walking the streets and stuff. then we we have something to talk about. But you wouldn't run this regression to begin with, because you already know from exploring the data set, you already know that quality control, that there's no quality here. Um, so the constant in that analogy would be for 1 bedroom or 0 bedroom. So if as we cross the y-intercept, this is 0 right here, right? So this is 0. And let's say this right here is 0. It doesn't make sense if this is 0 and that's negative. But I needed to show you that there's an independent somewhere. I guess I could have put the independent bar up here. Would have been more realistic for this particular gun analogy, this gun example, these outputs. But let's say down here is your predictor, and it's the price. It's $100, $200, or number of bedrooms. I'm sorry, the independent. It's your predictor. It's 1 bedroom, 2 bedrooms, 3 bedrooms, 4 bedrooms, 5 bedrooms, and over here is the cost. And so it's $500, $600, $700, $800, $900, a million, whatever. And you go up in your rent as you go up in the number of rooms of your house. So there are other explanatory variables. What neighborhood are you in? How big is your yard? How many people have ever died in your house? Are there like bullet holes in the windows? Is it carpet or wood? When was the last time the outside was painted? um 2-story or 1-story. There's all of these potential predictors, and if you don't control for those, they become confounding variables, right? They become confounding variables if you don't control for them. But a simple linear regression isn't controlling for anything. You're just looking at the relationship between two variables: your predictor, or your independent, number of bedrooms, compared to your dependent, cost of rent. And so with each additional bedroom, you expect the cost of rent to go up. Now, what you're seeing here is with each additional unit increase, which isn't 1 bedroom to 2 bedrooms, 2 bedrooms to 3 bedrooms, you're seeing 1 gun per 100 people to 2 guns per 100 people, 909,000, 910,000 increase. Body, death count increase, and that's ludicrous. Because the data don't lend themselves to regression analyses, you can't trust your findings. Do you get statistics that you can say on the news? Sure. Is that valid? No. And you know that it's not when you start analyzing what those distributions look like, and just look at that constant. It's so ridiculous. And so in the regression model, really what you're doing for a simple linear regression is you begin with the y-intercept. You don't need to do this on a test. This is just telling you what this is. And then with each unit increase, what happens. So there's your unstandardized beta. Now what your standardized beta is over here, this is movement of your standard deviations. So how many standard deviations you move, that doesn't really mean anything to anybody. Well, with each additional bedroom, we move a half of a standard deviation in rent. The hell? I don't know. How many dollars is that? It's a half a standard deviation. Okay, but my wallet doesn't disperse, cash in standard deviations. There's the unit is dollars, right? So the unstandardized coefficient is saying how many, what's the increase in the actual units of measurement over here. So with each additional gun per 100 people, it's the number of civilian gun deaths that you're seeing in those units of measurement. With each additional bedroom, this would be in the price, right? This would be the units of dollars, right? Unstandardized beta. You can report that if you want. I'll usually put that in the table, but I never talk about it because it doesn't mean anything to anybody. You can say the unstandardized beta. Yeah, that's a lot of syllables that people are like, unstandardized beta. But what it's describing is really easy to understand. With each unit increase in the predictor, the dependent variable increases by however many dollars, or whatever the units of measure of your dependent variable is. If it is pounds, if it's like, with each unit increase in height, with each inch you increase in height, this is like maybe like with each 1 pound you go up. With every inch you go up, you increase a pound or something like that. The unstandardized beta is in the units of measurement of your dependent variable. So it's a really nice statistic. This is how many standard deviations it moves. And if somebody tells me that, like, I'm pretty decent at statistics, and somebody's like, oh yeah, this moves by however many standard deviations. I'm like, I don't know what that means. I know what a standard deviation is, but I don't know what that looks like for how many dollars or how many pounds or how many points. Just give me the actual number that's meaningful that people talk in. Like how many points did you score? Oh, we were scored a half a standard deviation more in tonight's game than we did in last night's game. Okay, how many points? Don't tell me how many standard deviations you scored in basketball, right? It's gibberish. And well, it's not gibberish, but it's gibberish to almost everybody who's listening. This is not gibberish to anybody. A 9-year-old understands what this is. You just have to get used to calling it an unstandardized beta. But so that's what it means. And in this case, what we see is we begin with negative 5.5 million civilian gun deaths, and then for each additional gun per 100 people, we're increasing by almost 1 million. So that's what that's saying. The standard error is how much those betas vary. Report it, but you don't need to talk about it. Now they're huge, right? These are ludicrously huge, and so that's like a problem. But that's just how much you expect, how much error you expect in those betas. And again, the t-score, right? So that's just unstandardized beta divided by the standard error. Doesn't matter. Report it, but never talk about it. So this report, but never talk about, this report, but never talk about, this report, but never talk about, constant report, but never talk about. All you really report is what the predictor is, the unstandardized beta, the significance, and then the 95% confidence interval. We'll do that in just a minute. So this is, again, your standard deviations. How many standard deviations did you? Well, I moved to half a standard deviation. Okay. Like, what does that mean in terms of death? What does that mean? It doesn't. 20 minutes, thanks. So it doesn't actually mean anything to anybody unless you're looking at the outputs and it's not communicating the meaningful numbers, the standardized beta. So let's do a linear regression on slightly more sound data, slightly more sound. It's when we're looking at. So this is medical data, right? So let's look at total patient charges. And remember earlier the rib fracture stuff, thoracic epidural analgesia. So this is looking at this is the exact same data, but real data out of Indiana, major hospital, St. Vincent in Indianapolis, huge hospital, level 1 trauma center. It's enormous. They 365 days a year, they're helicoptering people in. It's one of those hospitals. And so TEA, pulmonary contusion, that's whether people had a lung bruise, right? Number of ribs fractured. Did you fracture 1, 2, 3, 4, 5? How many ribs did you fracture? And what's your age in years? These aren't thresholds, right? You can see there's scale data. So this is a multiple linear regression. There are multiple predictors and one dependent variable. The dependent variable is cost of care. Now it's still skewed. Cost of care is skewed, right? It's going to be dragged off to the right. There's a positive skew. It's going to be dragged off to the right. But this is better than the gun data. And so age, number of ribs fractured, pulmonary contusion, and TEA. Now what you want to do is you click on the statistics button, and over here you click on confidence intervals. Both of these should already be selected. Those should already be checked. So just check the confidence intervals, and this will give you a 95% confidence interval. So you click on that, and then just click on OK. The only thing you need to change in your regression analysis, unless inflation factors, if there's other stuff you get to look at, but we're not going to talk about those here in this class. And so what you want to do is just statistics, 95% confidence interval. Now you could change that number. You could highlight right here and delete it and put in 99% confidence interval or 90% confidence interval. That's fine. 95% is almost always what gets reported, but not always. So hit continue, you hit OK, and somebody's unmuted and there's conversation going in the background. So just make sure, unless you're about to chime in for a question. It's a very quiet conversation. Okay, so this is the output, right? This is the output that you see, and just remember to mute yourself. If you're unmuted, mute yourself, just for the sake of distraction. And so, does a 95? Okay, so somebody other than me is talking. So if you just look at your mute box, and if you're not muted, mute yourself so that we can all hear. And focus. Does 95% confidence interval correspond to a 0.5% significance level? Yes, 95% confidence interval does correspond to a 5% significance, but you're 95% sure that the true population mean falls within those two anchor points, right? These lower and upper bounds. Think of it as the parentheses around where the true population value falls. So you're 95% sure, 5% unsure, right? So it's 5% likelihood of falling outside. Go resample, rerun the experiment, get a brand new group of subjects, of patients being tested, and you will see what you should see is falling within the unstandardized beta, falling within these two ranges. So model summary, right? Pay attention to the R squared. Now the R squared is only 0.9, right? So that means 9% of the variance, 9% of the scatter in dollars is explained by this collection of predictors. That's a low R squared. So other variables are explaining 91% of the variance, 91% of the scatter is being explained by other variables. So down here, the overall model is very highly significant. And these are the significances um, of the cost of care. Now, when you see the constant, that's actually reasonable because the average cost of care was over $80,000, like $82,000 is the actual mean cost of care. And so the constant, is that like a perfect constant? No, but it's not ludicrous, right? It's not like the cost of care begins at negative $5 million. It's not like the gun database. The mean cost of care in this particular group was I don't know, 80 whatever thousand, 82,000. I don't know what it was. It was something like that. It was relatively close to the constant. So you report the constant, but you don't talk about it. You don't have to talk about that constant. So age, with each additional year of age, what you see is a $778 decrease in total patient charges. P equals 0.000, which means less than 0.001. Question, so would the higher the confidence interval mean the larger the range? The way I think of it is, if you are more confident, then there is a larger range of values that the true mean can be in, but I'm not sure. No, so it's actually going to be a narrow, the more oh, I think I see what you're saying, and the answer is yes. So if you're 99% sure, yeah, it'll be a broader range. If you do a 99% confidence interval, then you're 99% sure that the true value. So over here, we're negative $778 for each additional year of age. Now, the older you get, the more likely you are to die early, and death has a price tag, but staying 12 extra days in the hospital has a bigger price tag than dying. There's something very cold and calculated about medical billing, but with each additional year of age, it actually becomes a little bit cheaper, holding constant number of ribs fractured, whether they have a lung bruise, a pulmonary contusion, and the type of care, whether it's thoracic epidural analgesia or just like an IV morphine. That barely works. Other than making people feel good, it's not really a useful therapy. So age, the true population value, not exactly what we saw in this sample. This is the exact value down to the penny, down to $778.21.4, right? So that's what we see in this particular analysis. But in the larger population, inferential statistics, what do we expect to see? Well, something like this, somewhere between bringing the price down by $1,100 and bringing it down by $450. Now, if we're going to do a 99% confidence interval, what that question was about, we're 99% sure, it's a broader range, right? Because you're more sure about less accuracy. Now, if it's a 90% confidence interval, this is going to be a tighter range. If it's like a 75%, I'm 75% sure, you can get a pretty narrow range with like an 80% confidence interval or something, but 99% confidence interval, it's going to be a broader range. So number of ribs fractured. With each additional rib fractured, you increase the cost of care, holding constant age, pulmonary contusion, and whether they get thoracic epidural analgesia. Hold all of those constant. Those are not confounders here. With each additional rib fractured, you increase the cost of care by about $8,300. P is less than 0.001. So we are there's a 0.1% chance that we would observe something this strong or stronger, something of this financial clout, or stronger than that, of this value or greater, if the null hypothesis were true, if number of ribs fractured and patient charges had nothing to do with each other, holding constant age, pulmonary contusion, and TEA. So very, very confident. And this is the 95% confidence interval. We're 95% sure that the true population value, not in this sample, but in the population, that this is the actual effect, falls somewhere between those two anchors, somewhere between those two bounds. Your increase with each additional rib. So you go from 3 ribs fractured to 4 ribs fractured. You expect the cost of care to go up between $6,000 and $10,500 for the average person, not just the people in this sample. Now, pulmonary contusion, that's increasing it a lot, right? So you're increasing by between almost $24,000 and $57,000. P is less than 0.01, but that's a 0-1. Right, this is you don't or you do have it. This is you can increase by 10 ribs. You can go from 1 rib to 11, and so increase this tenfold, right? If you're increasing by 10 ribs, then you're looking at like $83,000, not 8,300, but 83,000. And so you add another 0 right there. So this is potentially more meaningful than this, but you have to go up a lot of ribs to get there. So this is reading a multiple linear regression. That's how you read that. Now, a logistic regression, this is what we'll kind of finish on, is the idea of logistic regressions. Is how much time do I have left? Do I have more than like 5 minutes? Am I down to like 2? 10. Okay, good. We'll actually finish the slideshow then. So logistic regression is the odds of an event happening, the odds of mortality, the odds of whether it rains. Is it going to be rainy or sunshiny? The odds of whether something is true or false, the odds of whether you win or lose. You could do this for the Super Bowl. You could do this for, the NBA or the World Series or whatever. You could do this for what are the odds of winning and losing, and you can come up with your own prediction model and then try to like beat the odds in gambling. Fine, you could do that, and you could probably come up with pretty good your own pretty good model. If you have some information that the point spread isn't accounting for, the odds of being pregnant or not. So the odds, it's a yes or no, it's a 0 or 1, it's a true or false. There's only 2 possible options in a logistic regression. So analyze regression. This time, instead of doing linear, right, do binary logistic. Linear, remember, your dependent variable is continuous. Binary logistic, your dependent variable is binary, right? And so you just put your dependent variable up here in the dependent section. We're going to do the same thing. We're going to do literally like the exact same, pulmonary contusion, TEA, number of fractured ribs, age. This is the exact same collection of predictors that we just did for finances. But the difference, we're looking at mortality now. We are not looking at the dollars. We're looking at whether the patient lives or dies. And so your dependent variable has to be binary. They live or they die. It's not like Princess Bride, mostly dead stuff. This is yes or no. 0 is they don't die. 1 is they die. That's how I coded it. I always code 0 is no and 1 is yes. And so then you want to click on the options. So click on options, and over here you see confidence interval for EXPB, exponentiation of beta. That just means odds ratio. It's always reported as EXPB, but how you report it is odds ratio. How you see it in the literature is odds ratio. You never see it reported in this way. You see it reported as odds ratio. This is just what SPSS says. So click on that, hit continue, and then you hit OK. And this is your output. There's a couple more tables. What are some other variables? Hold on, let me get the. What are some other variables other than mortality? Anything. I mean, you could do whether patients stay overnight, yes or no. You could do whether somebody gets injured. Let's say it's an athlete. What are injury predictors? This is an analysis you could do if you want to do like Proteus testing and then wait for people to get injured and say, aha, I know what predicts injury. It's this range of motion combined with power parameters with early acceleration or something like that. And you could say whether someone gets injured, 0 or no. So with each additional watt of power output or acceleration or something like that, you're increasing your odds of pitching injury by 2% or something like that. Anything that's 0 or 1, yes or no. What are the odds of winning tonight's game? Well, let's control for, is it a home game? Yes or no? Let's control for who the other team is, what their ranking is, right? Their first or 20th or whatever. How many players we have on the disabled list? How many, whatever your, how many miles we had to travel. Is it 0? Is it 100 miles? Is it a home game, or is it, would you have to fly on an airplane? Code for all of that stuff and then predict whether you're going to win the game. So that would be something in this case where it's just a prediction of, does the patient die? Real data, right? These are actual patients who died. And so this is, again, I'm going to talk about these things from the sort of cold calculated perspective, but it's a lot of what you're analyzing. These are human beings. These are like somebody's mom or kid, right? So you'll see a Nagelkirky R squared. That's your R squared that you can report. It's called a pseudo R squared. And whenever you see Nagelkirky, right, all that means is you've run a logistic regression. And this is a version of scatter, a version of variance. Now, this is your predictor accuracy, predicting with 93.4% accuracy of whether the patient walks in the door. You haven't done anything to them yet. You haven't done anything. They've walked in the door and you want to know if they're going to survive. You can predict with 93.4% accuracy whether they're going to die. These names are absurd. Yeah. Nagelkirky. They're just reading the comment box. But variables in the equation, what you're looking at is age. With each additional year of age, you expect the odds of mortality to go up by 2.1%. Multiply the baseline odds of mortality by 1.021, that's 2.1% increase in the odds of mortality. What's a 95% confidence interval? Oh, between a 0.8% increase and a 3.3% increase with each additional year of age. So if the person goes from 20 to 30, right, multiply that by 10. So now we're looking at something real in the odds of mortality. You go from 21 to 22, it's not really affecting you. Number of ribs fractured with each additional rib fractured. And this is just telling you, this first column over here is positive or negative. TEA is negative, what its effect on mortality is. So number of ribs fractured with each additional rib fractured, there's a 20% increase in the odds of mortality. There's a 95% confidence interval, and there's less than a 0.1% chance that we've observed something this big or bigger if the null hypothesis were true. The null hypothesis being number of ribs fractured, having nothing to do with mortality. Pulmonary contusion, that's a 2.4-fold, 2.5-fold increase in the odds of mortality. Going from a 42% increase up to a 4.3-fold increase in the odds of mortality. If someone shows up with a pulmonary contusion, holding constant, number of ribs fractured, age, and TEA. Now, TEA is reducing. There's a 95% reduction in the odds of mortality, holding constant those three variables. So these are the we're going to go through regression more. Don't worry, we'll do some more of that. As I introduce it once, we don't leave it alone forever. But the analyses now: descriptives, frequencies, t-tests, chi-squared, building table 1, and getting more specific. So this is just evaluating the overall sample and looking at the characteristics of it. You can put bivariate correlations into this group too. But there's also linear and logistic regression as we start to explore the landscape with a little bit more detail, a little bit more precision. So what you do in lab 2, as you conduct lab 2, take the data set. There's a few databases that were uploaded. And just splice them up and look at specific just English speaking countries or just American. There's 2 Americas, whatever. Not like the John Edwards version of 2 Americas, 2 continents, Amerigo Vespucci. But just European countries or just countries with populations of over 10 million, or you can look at, you can eliminate countries. And remember, this picking and choosing is how people enforce their biases often. John Lott Jr., that UCLA economist, remember he was looking at particular districts and gun control from 1977 to 1995. He was looking at that little area. I'm like, well, why did you pick those? Well, because if you look at other areas and other years and stuff, it doesn't uphold his hypothesis, right? Ansel Keys, very famous researcher, cover of Time magazine. It's not anymore, but he did the 7 countries study talking about fat and cholesterol and heart health and all that stuff. And why did you pick those 7 countries? Why did you pick this particular region and stuff? Well, those are more likely to agree with his hypothesis, right? Maybe you can rerun it and do like, let's do the 4 countries study and look at 4 countries that totally disagree. So you can do that here. This is how people enact their biases. They do inclusion exclusion criteria and get really narrow with, let me pick the specific subject subsamples that agree with me. And so you can do that. So I uploaded a second version of the, or Nathaniel did. I purged and Nathaniel uploaded a second version of the database where certain countries were removed, and I reran the bivariate correlations. And so in the original version of the database and in the new version of the database, some of it's a little bit different. Percentages of homicide by guns. Well, it's a different story. We have a very significant one, and we have an insignificant one. And so how you start splicing this stuff up. So in lab 2, you will make a table 1, same thing. And then your regression analyses. You'll do some regression analyses to find either pro-gun or anti-gun findings. And feel free to do a no relationship finding too, if you want to show all 3 from the same database. But the more interesting of findings that you can extract, the better, because that's what people want to hear on the news. That's what people want to see in print. That's what people want to hear in conversation, is really interesting things. Boring stuff, people don't really care about. Boring stuff is often true. Well, I'm not saying it's often true, but boring stuff, people aren't trying to dazzle. So there's no, if you're just going to go be boring, there's really no incentive, right? We incentivize the spectacular. Audiences, whoa, you get that like Macaulay Culkin Home Alone response with spectacular. That's a reference. I don't know if anybody knows, but you get the idea. The more spectacular your findings, the more interesting they are, and the more likely people are to repeat. Now they're going to be false because this is a ridiculous database, but that's the whole idea. That's what you see on the news. All right. Do we have any questions? So which would be better, higher confidence interval with less precision or a lower confidence interval with more precision? That depends. It depends on the nature of the experiment. If the higher confidence, if it's like a drug test, it's pharmacological stuff and you're looking at some new drug and you want to be really sure. You want to be really sure this has a better effect than the previous drug or lower odds of side effects or something like that. Do a 99% in those things. If your data lend themselves to a 99% where you can still get a pretty narrow confidence interval, report that. But most people do a 95%. It just depends on what you're looking at. Feel free to do a 90% if what you're evaluating is a little bit looser or less critical. If there's some lethal thing, I want to be 99% sure, right? There's if there's the odds of mortality and use of this medication and is it going to kill me or something, give me like a 100% confidence. I want to be as sure as possible. So it depends on the nature of the question, what type of confidence interval that you should use. But most people report 95s. Occasionally you see 90 or 99. Any other questions? All right, let's get out of here. I will see everyone on Wednesday. Go do your lab and just get it out of the way. You can submit that as soon as you want. We'll talk soon.